Welcome everybody to another technical video from Nairo Research. I'm Srijit here. So today in this video session, we are going to brief you about reactive force field engine or ReaxFF, which is a molecular dynamics method designed to model chemical reactions by describing the formation and breaking of chemical bonds within a classical framework. So in AMS, reactive force field provides a computationally efficient way to simulate large chemically evolving systems such as those with hundreds or thousands of atoms on a modern desktop computer. So what are the key features and principles? So unlike the traditional force fields, they rely on predefined bond connectivity. Reactive force field calculates bond orders based on the distance between the atoms. This allows for a continuous description of bond breaking and formation, enabling simulations of complex reactive systems that would be too computationally expensive for quantum mechanical methods. So the total energy of the system is the sum of the various contributions, including term for bond energy, lone pair energy, van der Waals interactions, and electrostatic interactions. So the electrostatic component uses the charge equilibration formalism, which allows for the dynamic redistribution of partial charges as the atomic environment changes, or the redistribution with the atomic environment. So the applications including, as we discussed, that it's a versatile tool with a wide range of applications in both academia and industry. So its ability is to handle large-scale systems and chemical reactions, make it well suited for simulating processes such as in material science for studying polymers, batteries, and semiconductors, energy and combustion for modeling combustions of fuels and high-energy materials, catalysis and surface energy for investigating reactions on surfaces and interfaces. In nanoscience, it can be used for simulating the behavior of nanoparticles and nanotubes. And the advantages of Reax in AMS. So integrating ReaxFF in AMS offers several advantages. So you can see this is actually the GUI which covers reactive force field. So the scalability. So ReaxFF is computationally efficient and has linear scaling with system size and allowing the simulations of millions of atoms. So you can see in this interface, we are focusing on targeted molecular dynamics for a chemical reaction. So I'll brief you. And the transferability. The method has been parameterized for a wide range of elements across periodic table, including metals and ceramics. User-friendly interface. So this is actually the user-friendly interface GUI, which simplifies the process of setting up, running, and analyzing reactive force field simulations. And speaking about the advanced tools, which AMS provides additional tools for analyzing reaction pathways, example the ChemTracer, and reparameterizing force field to better describe specific systems. So this is actually an example which we are going to discuss in this typical technical video, that how a reaction can happen in this with the reactive force field as we discussed. So I'm not going to brief everything in clear because it is a time consuming step, but I can show you that what are the inputs. So here we have taken water molecule and a propene system, which will form one propanol as well as two propanol systems. So how this can be done with reactive force field? Obviously, the molecular dynamics is the methodology. We have to select the force field, the respective force field. So this is actually the force field library where we can select the force fields as per our requirement. So as I mentioned earlier, if you want to reparameterize the force field, which force field you want to select, you can do the reparameterization using your params engine, which I will discuss in the coming series. So after selecting the CHO force field, we can then change the task to molecular dynamics. So it's already, I have calculated with the default settings as per the tutorial case study. So since it's a smaller system, we are limiting the steps around 3000 and the sample frequency. The initial temperature is around 300 Kelvin, and we are using the thermostat NHC, and we are arranging the inputs as per the tutorial case study. And after finishing it, so we will be executing the calculation, and the exact output will be like this. Since I already run the calculation, so the output, how we can visualize this through the MS movie. So it will take a few seconds to load up. And now you can see, let me delete this graph and add this graphical representation. So it will take some time. So you can see that how that reaction is happening. See. So at the bottom you can see the number of frames and geometry. So this is the way that we can understand that how the reaction is happening using reactive force field. So one propanol is formed and then two propanol. I think that the graphical representation engine. Yes, this is. So I will show it one more time. So in the first stage, this is actually the transition 1, where you can see that how that one propane is forming, and then the second transition state, not the state, transition or transformation, where water molecule and propane system is forming the second. See, it is right now, and now it is forming this 2-propanol. So this is actually the method, one application of a reactive force field engine to understand how we can perform the reaction or bond breaking and bond formation using reactive force field. Okay, thank you for right now. So I request you to kindly subscribe our YouTube channel as well as our LinkedIn page. Thank you.